And all right, good afternoon. Let's continue on with our discussion of transistors, specifically BJTs, bipolar junction transistors. And let's switch over to the class notebook. Oh. And let's see. Share. Okay. So we introduce the topic of a three-terminal, two-junction device, right? Known as a bipolar junction transistor. They come in two flavors, NPN and PNP, depending on the fabrication of the device itself. So it's two PN junctions connected back to back, right? Right here, the fabrication of the device. I think we were rushed, so I'm going to just cover this a little bit. This is a side view of the device, and this one shows a NPN transistor, right? NPN indicating the three layers of the fabrication material, right? So typically the way this device is fabricated is, if you think of it as a slice of silicon wafer, and we call it a wafer, so slice of silicon, and you're going deep into the surface. Now, these silicon wafers, they are not that thick, right? They're only 500 microns thick, which is basically 0.5 millimeters. You think of the mechanical pencils that you use, right? Mechanical pencils are 0.5 or 0.7. 0.5 is 500 microns thick. That is the thickness of that silicon wafer, okay? And so this is basically showing you a cross section. This is probably less than like 3 or 4 microns, if that, not even that much. And so the entire thickness of the wafer is like 500. Okay, so we're only using the top less than 10% of the top surface. Anyway, so to make an NPN device, we start with the N-type material. N-type meaning you have a silicon material that is doped with. Anyone remember? If it's more negative, well, you're on the right track. If it's more negative, what does it have an excess of? If it's excess of electrons, then it's column 3 or 5, column 5. So column 5 of the periodic table. So anyway, one of the materials from column 5, more likely boron. Boron is a very good impurity and dopant that we use for semiconductor fabrication. And so the entire silicon wafer has a concentration of boron, right? And that is going to form our collector. So in this case of the NPN transistor, this will be the collector, right? The three terminals of the transistor was the emitter, base, and collector. So the collector is basically the entire material. Then you create hole openings in that silicon surface, and you implant P-type material in there. P-type material will be from column 3, phosphorus. Let's see, what else? Arsenic. No, arsenic. I'm confused. I need a recap of the periodic table. But anyway, it has 3 electrons on the outermost surface, so it's an excess of positive charge, so P-type material. Now, the doping, meaning the amount of carriers that are available in the collector, is less compared to the base. So this one we say is lightly doped. That's right, we call it doped, lightly doped. Lightly doped. So it does not have that many charge carriers. Okay. Physically, it is the biggest surface area in the device, right? So the collector is the biggest, but it's the least, it has the least amount of charge carriers. If it's N-type, we're talking about electrons. If it's P-type, we're talking about holes, positive charges. But it is lightly doped, meaning it has the least amount of charge carriers. Then comes the base. The base is smaller than the collector. And again, this is a blown up section, so it seems as if it's really, really big, but it's not. This is actually very enlarged and not to scale. In reality, this is a very thin layer. Actually, very, very thin. Running in nanometers, actually. Again, there's a specific purpose for it. So, very, very thin layer. And physically, since it's very thin, it has slightly more doping than the collector, still not a lot. And then once you have that entire opening and now you have a PN junction, you open it, you open a second opening on the top in the middle of the base, and you create your emitter junction in there. Okay, you create your emitter junction in there. And the emitter is the smallest of the three, but it's the most heavily doped, terminal of the device. Okay, so this is the most heavily doped. And because it's the most heavily doped, it has an excess of charge carriers. Excess of charge carriers. Now, when we say charge carriers, we are referring to both holes as well as electrons, right? Remember, the name of the device, bipolar junction transistor, comes from the fact that the current and the charge carriers are both positive as well as negative. Okay, hence the name bipolar junction transistor. So, collector is physically the largest, yet it is it has the least amount of charge carriers. Base is smaller than the collector, has slightly more charge carriers, and emitter is the smallest of the three, but it has the most amount of charge carriers. It's the most heavily doped. So you would often see this as being referred to as N plus, and the emitter would be referred to as N plus plus. Plus and the plus plus is just showing you that it's very heavily doped. That's all it means. This one might be referred to as P plus. If it's PNP transistor, if it's a PNP transistor, and this is the emitter, then this would be P plus plus, this would be N plus, this would be P plus. All right, any questions? Now, why am I going over all of this? The purpose is to show you that the operation of a transistor is not modeled after two back-to-back diodes. Okay, it's not modeled two back-to-back diodes. So you cannot simply take two diodes and say that's how the transistor would work. And one big important factor in that is that the base is physically very, very thin device. Okay, the base layer is very, very thin. So let's see how that's going to work out. Now the emitter base junction, as you will see, will work like a two diode, but the collector base junction, not so much. So when we actually want to operate a transistor in a circuit, we're going to apply a certain amount of voltage to it. That voltage is external to that transistor itself. It's external to the device, right? And so we call that external voltage as a bias. That bias is basically a bias, is also known as the biasing voltage. And what you're doing is you're programming the transistor to operate at a certain point. Remember that load line, right? We're going to see it again. But in the diode, remember the load line where we actually decide the value of the external voltage battery, and it moves the operating point along that load line, right? And that is what we're going to do again for the BJT. So this biasing voltage, what it does is it sets up the operating point for the transistor. And more importantly, it also provides the currents needed for the device to operate. Okay, so it sets up the operating point and provides the current that the device needs to operate. Now, The operating modes, sorry, was there a question? Yes. The operating mode and also provides the current for the device to operate. Yeah. So depending on the biasing, there are 3 different kinds of operating modes, and we will see each one of those in just a few slides. But take a look at this figure. Now, everything that we are talking about refers to the NPN transistor, but the exact same is also true for the PNP transistor also. The only thing is everything will be reversed, right? Everything will be reversed. So if you look at the base emitter junction, you have a PN junction, and you have a positive voltage being applied to the P-type material, and the negative voltage being applied to the N-type material. So what is the status of that PN junction? PN junction, forward bias. It's forward bias. So this junction is forward bias. Whereas if you look at the collector and emitter junction, what do you see? It's reverse bias. So the collector base junction is actually going to be reverse bias because you have a positive voltage being applied to the N-type material. The 3 currents that are related to each of these terminals are simply referred to as IC, IB, and IE, base current, collector current, and emitter current. And the 2 voltages that are the important characteristic are VBE and VCE, meaning the base emitter voltage and the collector to emitter voltage. And you already know the answer to one of these values. What is VBE? Value of VBE? Or what should be the value of VBE? It's the diode follows by a drop. Yeah, 0.6 to 0.7 volts. So if the transistor is biased such that the base emitter junction is forward bias, then VBE will always be 0.6 volts. Yes. I know it's not very clear from this diagram, but you will see it from the next one. We'll actually apply a biasing voltage like this. So this is actually just indicating that it's being measured across the collector and the emitter, but the actual biasing is between the collector and the base. And we apply a positive to the N and a negative to the base. You can also change that biasing. You can have both junctions forward bias, and that will result in a specific operating mode. So these are the 3 voltages and the 3 currents that are associated with a BJT. Okay, you have VBE, VBC, VCE. Each one of those is measured with respect to between 2 terminals. And then you have the base current, the emitter current, and the collector current. If you look at the current directions and apply KCL at the transistor node, what do you get? You have IB coming in, IC coming in from the top, and IE leaving, right? So IE is the sum of IC, the collector current, and the base current. Okay. If you take a look at the voltages and you apply KVL around that loop, it doesn't seem as if there's a loop in there, but you can think of it like this. You have collector here, you have base here, you have emitter here. So if you measure the voltage from here, VCE, it stands to reason that it is VCB plus VBE. Does that make sense? So these relationships are going to be very important when you perform analysis. IE is equal to IC plus IB, VCE is equal to VCB plus VBE. And we will dive a little bit into the device physics. Not much, just a little bit. I will talk about these in the next few slides. Any questions? Okay. All right, so basic operation of a BJT transistor can be explained by this diagram. I have another one after this one that I like very much. I will bring that up and talk about that also. But what essentially happens is you have charge carriers from the emitter. Charge carriers from the emitter will actually go into the base region, and from there, they're going to go into the collector region and go out through the collector. Current is always, if you remember, current flow is always the opposite of the flow of electrons. So the electrons are actually going this direction, current is actually going the opposite, coming out. And so you can see that IE is made up of IB plus IC. Now, an even better diagram is right here. Not being able to locate the source of this diagram. I don't know which book or which journal paper it comes from, but this is actually from Wikipedia. Now, you don't want to trust, it's a starting point. You always want to verify your sources. So I know that this is correct because I know the operation. As I said, if I knew what the original source was, I would use that. But unfortunately, I don't. So, in the interest of disclosure, I'm going to tell you that this comes from Wikipedia. But this diagram, if you look at the circuit diagram, you're applying, and remember I just mentioned that collector is connected to positive and base is connected to negative, right? So that's the reverse bias. We have VBE here. Now it says VBE and VCB, right? It gets confusing because VCB is actually the voltage that is being measured. Okay, that's not the voltage that is being applied. Typically, when we apply, like if you're doing your labs, this voltage will be known as VCC, and this voltage would be known as VEE. There's a specific reason for that, but let's not get into it right now. Suffice to say, there is an external voltage that you're applying between the base and the collector, right? That reverse biases that collector base junction. You apply a forward bias to the emitter base junction. Remember, this is N, P, and N. So negative being applied to the N-type material. What charge carrier is the majority carrier in N-type material? Electrons, right? And you apply a positive bias here. What happens to the electrons? They're going to cross over the junction because they're forward bias. At the same time, you have holes here that are going over here. Because in P-type material, majority carriers are holes. You have current going this way, bipolar current flow because of both carriers. All right. Now what happens? This is exaggerated. The base is not this wide. It is very, very thin. Some of the electrons, very few electrons, will recombine with the holes that are present in the P-type material. And this is the reason for that very thin material and slightly less doping. There are not enough holes available for the electrons to recombine. Whenever they recombine, you have, hole is an empty spot. Electron comes and goes into the empty spot, that's gone. That charge is gone, right? So some of them combine or recombine with the holes, but there's like tons left over. What happens to those? This junction is reverse bias, meaning there's a positive charge attraction at this terminal. So all the electrons are pulled here. Make sense? So majority of the carriers that are coming from the N will go into the P-type. Some of them are lost to recombination, but a majority of them cross over the reverse bias barrier and come over on this side. Yes. Um, that's a good question. No, it is a necessary part in essence, yes, because you will see that the collector current depends on IB. Okay, a small change in IB will create a very large change in IC. So it is a necessary part of the operation. Yes, most likely. Yeah. All right, think on it for a few seconds. Let me know if you have any questions. Oh, wow, it's already 2. I was just getting started. Okay, so the result is, of course, that IE is equal to IC plus IB. Does that make sense now? Okay, so as I said, I mean, the image is from Wikipedia, but it's absolutely accurate. All right, we'll end class here today. I'll be in my office later. You got it now? Okay, all right. So just send me an email whenever you're able to like connect back to internet, and then I'll open it up and we'll upload it there. All right.